Hello, everyone. Let's take a look at the Achieve 3.9 homework assignment. I think I will go ahead and just maximize my document camera screen because I have all the problems written down in this section. If for any case we need to refer back to the Achieve assignment, I'll do that on the particular problems, but I wrote everything down pretty much. So I'll just go ahead and maximize this so you can see the screen a little larger. The first problem asks us to take the derivative with respect to x of 9x times the natural log of x minus 2x. Well, we know in this section that the derivative of the natural log of x is simply 1 over x. That's the only thing new in this problem. Other than that, you also have to understand that there's a product rule going on with the first term. So when I take the derivative with respect to x of this group, I can say, okay, the first term, derivative of the first, 9, times the second, plus the first term of that term, 9x, times the derivative of the second. Well, derivative of the natural log of x is 1 over x. Now, the derivative of the second term in there, derivative of 2x with respect to x is just 2. So we put our minus 2 there. Now, this is a good answer. I went ahead and made it a better answer by just saying I know that 9x times 1 over x, that's 9x divided by x, that's 9. So those last two terms are really just plus 9 minus 2, better written as plus 7. So final answer of 9 natural log of x plus 7. For our next problem here, we have an exponential function. So what I'm wanting you to remember now, the derivative of every single solitary exponential function in existence is that exponential function times the derivative of its exponent times the natural log of its base. If you remember this, you will never miss the derivative of any exponential function. Now, we never have to worry about that last step whenever we deal with the exponential function base e, because we know the natural log of e is just a factor of 1. But any other exponential base, you most certainly have to worry with that last step. So the derivative of 5 raised to the x to the 8th power is 5 raised to the x to the 8th times the derivative of x to the 8th, which is 8x to the 7th, times the natural log of the base of the exponential function, natural log of 5. That's pretty much the only way that you can write this answer. Please don't make the mistake in saying, well, should I multiply that 8 by that 5? No, that 5 is the base of an exponential function with an exponent of x to the 8th. 8 is not. So you cannot really multiply anything. I would just leave it like it is. Now, for the next problem, we had the natural log, or I had the natural log of 4x squared minus 9. So what I've shown here, and the way that I've shown this, is that I'm wanting you to remember the derivative of every single natural logarithmic function in existence is 1 over what's inside of it. But now, what's this remaining part? Well, that's due to the chain rule. So you might say, well, the derivative of the natural log is 1 over what's inside of it. But the chain rule says you always have to multiply by the derivative of what's on the inside. So I did that. The derivative of 4x squared is 8x. It's probably better if you just go ahead and write the 8x in the numerator in your very first step rather than out like this. I was just showing derivative of any natural log is 1 over what's inside the natural log. And then thanks to the chain rule, we say times the derivative of what's on the inside. That's where the 8x comes from. But that derivative of the inside always goes up in your numerator. Final answer like that. For number 4 here, we have 6 times the expression, the natural log of 2x, all raised to the 4th power. Gorgeous chain rule problem here. I need to think of this as a 1, 2, 3-layer chain rule problem. So the outer layer is the power on this group. So I can say, okay, power rule. 4 comes down, multiplies the 6 to give me 24, times this group to the 3rd power. But then you say, well, now times the derivative of what was inside of that. The next outer function is your natural log. You say, okay, derivative of every single natural log is 1 over what's inside the natural log. So I'll put a 2x in the denominator. Now, where did that 2 in the numerator come from? Because after I did that second step in the chain rule. The third step would be to say, yes, the derivative of the natural log is 1 over what's inside the natural log, but then you need to multiply by the derivative of what was inside of that natural log, which is 2. Just like the last case where I moved the 8x to the numerator, I went ahead and moved that 2 to this numerator, makes it look better. Now clearly those 2's are going to cancel and I'll have an x in the denominator, and that's the only term I'll have in the denominator throughout. So I just wrote my final answer as 24 natural log of the group 2x quantity cubed all over x. Now, if we, let's see if that's a little blurry there. If we try to look at the next problem here, similar to number 2, it's an exponential function. Now my exponential base is base e, and it's just being multiplied by 4. Please understand, 4 is not the exponential base. It's just the constant multiple of the exponential base. So I can say, okay, derivative of any exponential function is that exponential function times the derivative of its exponent. Well, its exponent was a group to a power. So I can say, okay, I bring the 8 down in front, times that group to the 1 lower power, times the derivative of what was inside of that group. But the derivative of the natural log of 5x would be 1 over 5x times the derivative of 5x, which is where that 5 came from. So the derivative of the natural log of 5x is just really 1 over x. Those 5's are going to cancel. So yet again, and sorry about this right here, the whiteout was not easy to write over. That's supposed to be a 32 there. Where that 32 comes from is the 8 times 4 is 32 times your exponential function e to the group natural log of 5x quantity to the 8th times the other factor in that numerator of the natural log of 5x raised to the 7th, and then all over x. Again, keeping in mind the 2 5's just canceled out. Final answer there. For number 16, we have for number 6, we have 16 times the natural log of the natural log of 7x. So I'm thinking of this is a function inside of a function inside of a function. I better be able to distinctly show the 3 layers of the chain rule in this problem. Otherwise, I've not accounted for my derivative. So I can say, okay, the first thing I do, take the derivative of the outermost function. Well, that's 16 natural log of this group. Derivative of every single natural log in existence is 1 over what's inside the natural log. So I just said 16 times 1 over the natural log of 7x. Now, times the derivative of what's on the inside. Well, what's on the inside is a natural log. The derivative of every single natural log is 1 over what's inside that natural log. And then you can say, okay, now the chain rule would still say times the derivative of what was inside of that group. Yes, derivative of 7x is 7. So that 7 is going to cancel with the 7 in the denominator there. This is all just going to be 1 over x. Unlike my last 2 problems, though, there's something else in the denominator. I have a factor of x in the denominator, and I have this factor of the natural log of 7x. Looks like my only numerator is 16 for a final answer of 16 over x natural log of 7x. For number 7 here, we have the natural log of the group 4 times the natural log of x raised to the 4th. So again, this is tricky because of the chain rule. I have a differentiable function inside of a differentiable function inside of a differentiable function. This is going to be a 3-layer chain rule problem. Gorgeousness. So the outer layer, this natural log, and you say, well, that's easy because the derivative of every single natural log in existence is 1 over what's inside the natural log. So I got the first step, times. Second step. Well, now the second step is going to say multiply by the derivative of what was inside of that natural log. And I said, well, it's a group to a power. The power comes down in front, so times 16 times the group, the natural log of x raised to the 3rd. So this is the first layer of the chain, second layer of the chain, third layer of the chain. You say, well, now you have to multiply by the derivative of what was inside of that group to a power. Derivative of the natural log of x is 1 over x. Now, in this problem, a lot canceled out. Notice this natural log of x group cubed cancels with the natural log of x to the fourth, or it cancels with 3 powers of it. That's why you only have one natural log of x term in the denominator. I have an x that's going to go in the denominator, 16 divided by 4 reduced down to 4 in the numerator, and I have my fully factored and simplified final form of the answer. Good problem there. Number 8. This one's actually a little bit simpler. We just have a differentiable function inside of a differentiable function, so this is really only a 2-layer chain rule problem. You'd say, all right, first layer, derivative of every single logarithm in existence is 1 over what's inside the logarithm. 1 over what's inside. Now, times the derivative of what's on the inside. And I could have went ahead and put this derivative of the inside in the numerator. I was just trying to show this is my first step, times the derivative of what was in the inside. Derivative of 5x is 5. This 3 over x, it's better if you think of it as 3x to the negative 1. So then when you take its derivative, you can say, well, that's going to be negative 3x to the negative 2. Better written back as 3 over x squared in the next step. So I thought of this as 3x to the negative 1 for its derivative, negative 3x to the negative 2. And now I know this is going to belong in the numerator, so that's what I did. 5 minus, this is the same thing as 3 over x squared. I didn't want to put a negative exponent in my answer, though I'd say a cheat would be okay with it. It's sloppy. Now, in my denominator, I have this. I knew I could get rid of every fraction in that side of that fraction if I multiplied by x squared over x squared. So that's what I did, leaving me an answer of 5x squared minus 3 in the numerator and 5x cubed plus 3x in the denominator. And you could factor an x out of the denominator, but there's no reason to do that because nothing would further factor. And you can see that answer is precisely what I put in on Achieve, and Achieved liked that one. Now, let's look at my next page of work here, starting at number 9. We have an annoyingly easy problem. You say, wow, seriously? That's just an exponential function. So we say, derivative of every exponential function in existence is that exponential function times the derivative of its exponent, which is understood to just be 1 in this problem, times the natural log of its base. So number 9 is annoyingly easy and short. There's no work to show. That's it. So please remember, derivative of every single exponential function is that exponential function times the derivative of its exponent 1 times the natural log of its base. Done. Now, number 10, still easy, but at least it's a little more interesting. It's an exponential function. Derivative of every single exponential function is that exponential function times the derivative of its exponent, which is giving me 5 minus 2x, times the natural log of its base, natural log of 6. Final answer there. Now, what if we have a logarithm that's not a natural log? Well, I would like you to remember the change of base formula. If I have the log base 4 of any term, you can just say, well, that's the same thing as the natural log of the term on the end divided by the natural log of 4. It is. So all that you're going to have to do for any logarithm of any base is take the derivative the exact same way you would if it was a natural log, with the exception that you're going to put the natural log of the base in the denominator. So when I'm thinking about how to work this problem, I'm thinking, okay, how do I take the derivative of the log of 5x? Every single time, it's 1 over what's inside the logarithm, so 1 over 5x, times the derivative of what's inside the logarithm times 5, that's where the numerator came from. And then if it's not a natural log, you're always going to divide by the natural log of whatever the base is in that denominator. Again, that's just using your change of base formula. And then in this case, you can see the 5's cancel out. So you can say, well, your answer is 1 over x times the natural log of 4. Absolutely. And they labeled that derivative, in this case, the derivative of f with respect to x. Now, for number 12, If I have the log base 4 of the sine of 6x, again, no problem. I'm saying the derivative of every single logarithmic function in existence is 1 over what's inside the logarithm times the derivative of what's inside. Well, the derivative of sine is going to be the cosine of that angle times the derivative of the angle. That's where the 6 came from, chain rule up here. So now I can say, all right, that's the derivative. If it were a natural log, it wasn't a natural log. What's the only difference? Well, log base 4, you put the natural log of 4 in the denominator of this derivative answer, and you have your solution. Now, you could have left it like this. I just went ahead and said, well, cosine over sine is cotangent. So I said 6 cotangent, 6x all over the natural log of 4. This answer's fine. This answer's a little better. Now, they started asking some equation of the tangent line problems. No problem. So what if I wanted to know the equation of the tangent line? And let me go back and see, do they give you the y value at the point, or do you have to find that? I don't. So it's the equation of the tangent line of the exponential function 6 to the x, and they only give you the x coordinate, x equals 2. All right. So if f of x is equal to 6 to the x, I know the derivative of every single exponential function is that exponential function times the derivative of its exponent, which is 1, times the natural log of its base. That's where the ln 6 came from. Now, I know that the slope of the tangent line is nothing more than the derivative evaluated at the x value of interest. So I can say, well, all right, if I evaluate the derivative at 2, I would get 6 squared times the natural log of 6. That's 36 natural log of 6. Now, clearly the y value at the point is just going to be 6 to the second, or 36. So I said, well, my point is the ordered pair 2, 36. This is my slope. So my point slope formula, y minus y1, y minus 36, equals m, or slope formula, times the group x minus x1, x minus 2. And then they don't want you to distribute through since you have a complicated slope formula. Just bring the 36 over and you'll be fine. So final answer there, 36 natural log of 6 times x minus 2 plus 36. And you can see that that's precisely how I entered it in on the achieve answer there. Now, number 14, similar. It gives me another exponential function, and it's asking me to find the equation of the tangent line when x is 1. All right. So I can say, well, if now my function is 2 to the 3x, its derivative is going to be 2 to the 3x times the derivative of its exponent, 3, times the natural log of its base, natural log of 2. Now, the x value given in the problem was 1. So the slope of the tangent line is the derivative evaluated at 1. If you evaluate this at 1, you're just going to get 2 to the third power times 3. 2 to the third is 8 times 3 gave me the 24. And then I have 24 natural log of 2. So that's evaluating my derivative at 1. In order to get the y value, you would just evaluate your original function at 1. Obviously, that's 2 to the third, which is 8. So I have my point, I have my slope, I plug that information in. Y minus y1 is equal to m times x minus x1 here. And again, just like last time, keep the right-hand side as it is, move the 8 over to solve for y. And we have our final equation of the line there. It looks like 15 and 16 keep up the same stuff here. In 15, we have a slightly more complicated exponent. That's no big deal. We're asked to find the equation of the tangent line to the curve 3 raised to the x squared minus 2x plus 4 when x is 1. Okay, so looking at that, here's our original function. I can say, well, then my derivative is going to be that exponential function times the derivative of its exponent, which is just power rule, 2x minus 2, times the natural log of the base, natural log of 3. Now, this looks more complicated, but it's easy to evaluate. We needed to know the equation of the tangent line at 1, so I just evaluate my derivative at 1. And I didn't even have to do that very long because I just said, ooh, if I plug a 1 into this factor right here, it gives me a factor of 0. So it's irrelevant what it is there. 0 times anything is 0. So I'm going to say, okay, this is going to be an equation with slope 0. So the only thing I had to do is find my point. The y value of your point, you're going to have to plug a 1 into this equation. And when you do, it's 1 squared minus 2 times 1. That's going to be 1 minus 2 is negative 1 plus 4 gives me the 3 for the exponent. So I said, well, that's 3 to the third power, which we know is 27. So now it's just the equation with a slope of 0 going through the ordered pair 127. Y minus y1, y minus 27 is equal to m, which is just 0, so there's no need to put the x times x1, 0 times anything is 0. Now solving for y, you can just say, well, just move the 27 to the right-hand side. Your equation of the tangent line is going to be the y equals 27 here. Now for number 16. Again, it's giving us a function, and it's asking us to find the equation of the tangent line, this time when x is 1. So I needed to take the derivative, and I knew the derivative of every single solitary logarithmic function in existence is 1 over what's inside the logarithm times the derivative of what's inside the logarithm. Well, the derivative of 31 minus 15x is negative 15. So this is the derivative of that logarithmic function. I need to evaluate it at 1 to find the slope. Well, my slope is going to be negative 15 over 31 minus 15. That's negative 15 over 16. Now, this is the slope when x is 1. I need to know the y value when x is 1. So I just plugged a 1 into the original. 31 minus 15 is 16. That gives me the natural log of 16. So I have my ordered pair, 1 and the y value, the natural log of 16. I have my slope, negative 15/16. Plug that into your point slope formula. Y minus y1 is equal to your slope, negative 15 over 16, times x minus x1, x minus 1. Now you can distribute through the negative 15 over 16, or since we didn't in any of the other problems, I chose not to. I just left it negative 15 over 16 times this group. And another reason not to is you couldn't have combined that constant 15 over 16 with the natural log of 16 anyway. So I left it in this format, and I assure you that you liked the format of that answer right there. You liked it a lot. Now, for the remaining questions in this section, I guess it's just 17 through 23. I'll do that in another video just to make sure that Zoom doesn't cut me off. Look forward to looking at those with you. Please let me know if you have any questions.